Hello everyone. Today I want to run a demo to show how to use the kernel perceptron learning algorithm. Firstly, let's look at an example. We have a dataset of totally 8 points here. And our goal is try to find a classifier that could classify um, this 8 points into two groups, class 1 or class minus 1. Currently, you can see I already colored this 8 data point into two groups, the red group and the black group. Um, and the red group is the class 1 group, and the black group is the minus class 1 group. Okay, no, it's basically non-linear separable. If we want to do a boundary in this 2D space, probably something like a circle will do, right? But apparently a line cannot do it. So what are we going to do in this case? So firstly, there is a trick to do it. Um, the trick is we will try to define a map function. So currently we call all the position vector of current point. We call it vector x, and apparently x belongs to the R2 space. If we could come up with some map function that could map the position vector x into a higher dimension space. When I talk about higher dimension space, for example, a 3D space will be a higher dimension space. It is possible that the map result will be linear separable in that space. So here we have some terminology. We'll call the R2 space the input space. And we will call the space after we do the mapping, we call it the feature space. Yeah, I just want to let you know something. It is quite usual that if you find out in current space, the data point is non-linear separable. And if you try to map it to a higher dimension, it is quite common that the result will become linear separable there. Okay, so for example, let's do a experiment. So I'll define the mapping function as, so currently 2D space. Okay, so let's try utilizing this function. I'll do a table here. So the first data point, the position vector is 1, 0, and after we do the mapping, it's 1, 0, 0. The second data point, you see they overlap with each other. After we do the mapping, if I roughly draw it, the space become a 3D space, and we call it the feature space. Um, so imagine I draw it like this. You'll find that many output they just overlap with each other. So basically, they are 4 distinct point in the feature space. So one is over here, it's 1, 0, 0. But it includes already 2 data point there. And the other it's over here, it's 0, 1, 0. Also have 2 data point here. And then here and here, another 2 point. So it's roughly distributed like this. And now we can tell it is possible that we find a plane in this 3D space, right? Just imagine if I project this point and this point onto this plane. The projection is here, right? The projection is here, and apparently, it's possible that I find a plane like this that could separate the black dots and the red dots. And so I just want to show that after we map to this 3D space, the data become linear separable. If we want to do it in this way, the trick will be we define a mapping function. People usually call it phi x that could map the input space to a feature space. And then we can just do like a normal perceptron training. When this feature space it's linear separable. Yeah, it's great, right? Problem solved. But can we do better? Notice that in order to do the normal perceptron learning, we need to compute every single point in this dataset. What if this dataset is really big? It will involve a lot of computation here. So this is the space where the kernel trick will tap in. But before I introduce the kernel trick, I want to talk about something about dot product. We know that when we dot product a two vector, for example, A is x1, x2, x3, and B is y1, y2, y3. The result is it's just a number, right? It's just a number. It's some number. And in machine learning language, people call it scalar. Basically, it's just some real number. Okay. But if you interpret it from the geometrical view, we can use this scalar to measure how close related are these two vectors. We know that this equals the modular of A times the modular of B times the cos theta. So what does it mean if we try to interpret in this way? Say if A and B, they are tend to align with each other or tend to parallel with each other, then they will have a small theta, a small angle. In this case, the dot product, the dot product result will be a positive number. And it might be a large number. Like we know that it's less than or equal to the modular, the multiplication of their modular. If they are not aligned with each other, there comes a big theta, then the result will be less than 0. And of course, when they are perpendicular to each other, the result will be 0. So roughly, you can think it in this way. If they are close to each other, or when we say like they are close related to each other, we will say we will see the dot product is larger than 0. And if they are not close related to each other, the result will be less than or equal to 0. Okay. And just bear this in mind, and we're gonna take a recap on the dual form. On the dual form of perceptron learning. So just think dual form in this way. When we try to find a classifier, we just learn from the given data set. Okay. And for the given data set, we want to give each data set a say, but the say is different. Just like some point in the group, they are really critical. For example, this point here. So it just shaped the boundary heavily. So it have a very heavy influence on the classifier. So we want to give it a big say there. Some data point that is not critical at all, it's far away from the boundary, so we give it a small say there. So if in the primo form, we will describe our goal to find a omega or w or whatever, to find an omega that could correctly classify all the data in the set. But in the dual form, we just rewrite the omega in another form. We write it as we just write it in this form. Okay. How do we perform training? We look through all the data points and check if this condition is held. This condition, it has two people usually have two different ways to express this condition. It just means that we want to check, is there any misclassification? That is like it's the sign of this whole bunch. Equals to the sign of the label. It just means that did we clarify something here? Okay, so you can see, when we do the perceptual learning in dual form, something interesting pop up here. There are dot product appear in the dual form perceptual learning. And how does dot product related to kernel trick? Just wait for it. Now we talk about kernel trick. So recall that we have the feature space, right? The feature space, we have this. We only have this 4 distinct value. Each of the value have 2 points here. So 2 points, 2 points overlap here, 2 point overlap here, and 2 point overlap here. The feature space, it's a R3 space. So just imagine I randomly pick 2 vector. I call it V and V slash. From this A point, okay, from this A point in R3 space. We know that it's mapping from the original to the space, and if I call it the original mapping X and X slash, right? So we know that like we mentioned before, we care about the dot product, right? When we do the perceptual learning in dual form, so we will care about what is the dot product of V and V slash, and if we express it in 3D coordinate, it's actually corresponding to like let me just write the expression, okay? This is how I call them, but if I express them in the coordinate form, I'll just call my x1, x2, right? In original 2D, that's in the R2 space, and I'll call x slash s1 slash s2 slash. And the corresponding v is also corresponding v slash. So we know that the dot product of these two just equals to s1 slash square, s2 slash square, and square root 2, s1 slash times s2 slash. And if we expand it and try to calculate the answer, that's now something amazing happened here. It happens to be x1 slash plus x2 slash square. So it happened to be in the original 2D space, the dot product of vector x and vector x slash the dot product square. If we want to know the dot product in the feature space, we don't need to know what exactly v and v slash they are. We can calculate directly from the input space. We can just firstly calculate the dot product of x and x slash, and then we square this dot product, and we will get the dot product in the feature space we want. And we'll call this kx x slash. We'll call this the kernel function. So the trick of kernel function is just they save our effort to actually firstly try to map every point to a higher dimension and then calculate the dot product in that higher dimension space. We can calculate directly in our original space, the input space. So with this in mind, we can now still start to use the kernel tricks. So if we know that the dot product we want in the higher space could be calculated like this, it means that we don't need to do the mapping anymore, right? We know that in the perceptron learning in dual form in the feature space. Now with this equation hold, in the feature space, we know that previously our checking condition is this. But with this equation, we can rewrite the condition. Just rewrite it, copy everything. In next episode, we're going to use this dataset to run through algorithm kernel perceptron. If you find my video is helpful, like and subscribe. Thank you.